selections. So this is a little example we had. If we have already scaffolded a database that had an existing players and games table, and remember scaffolding is just the process of automatically converting tables into C# classes, objects that represent them. Then I can do something like something that looks like SQL, but it's kind of like reordered and close. So from P in players, join G in games, on, things that look like SQL. And then, so that's if I want to select P, which will give me the whole player object. But if I wanted to select, say, and this is like the library now, patrons, join, checked out. If I want to select the patron's name and the book's serial number. Remember, I can't really just do this, select p.name, comma, c.serial, because the query itself is an IEnumerable of what? You can't make an IEnumerable of multiple dynamic types. So what we do is we use these anonymous types to just create a new object, a new type right on the fly, where I just say select new with no type or name or anything, and then in braces I can just say it has a field called name and it has a field called serial. Okay? So, and then query is an enumerable, so I can do a for each loop, and we don't know what the type is inside of the enumerable. All we know is that it has something called name and it has something called serial. So I have to use var here. I can't say like for each thing X. I have to use var. And then finally, if we're returning this to like a web server that's going to take that information and produce some HTML or something. There's a lot of ways to do this. Our preferred way is JSON, because JSON has no types, it just has names. So I can just say, whatever names the web server is expecting, give it to it in JSON, and then it can go and draw things. So all we have to do is this function JSON, and then pass it in an array. And it'll automatically create an array, and automatically using this high-level language feature called reflection, it'll go in and figure out what all the types are and what all their values are in that array. Okay, so to get your minds working again after the break, I want to do a little exercise. So we're looking at the library table, just a database, just two tables. Super simple query that you could do like in your sleep in SQL, but the exercise here will be to translate that into LINQ. So I want a JSON array where each object in the array has this form, something called title and something called serial. So I want basically the serial numbers of all of the books in the library. So you'll have to write a LINQ query and you'll have to convert that to JSON, but we just kind of recapped how to do that. So take a minute with the people around you and work out an actual query. We'll type it up in Visual Studio. The main page of the web server is just going to pop up a browser alert that will show whatever we return from this controller. So I already have using library context all set up to go. Okay, so anyone want to give me their LINQ query, including the converting to JSON? Yep.
So I can give you a start just really please.
Okay.
So first we need to get the information we're looking for. So we're going to from T in titles, join I inventory.
From T in, so we need db.titles.
Yes.
And we can't just start with from, we need to do var, something, I'll call it query. So from T in titles, and then what was the rest?
Join I in inventory.
Join
Or
I
inventory.
in inventory.
And then we're going to say select view.
Okay.
And then we're going to pull out, we wanted the title of the serial. So we'll make member variables and assign to those.
Title equals T.title. Serial equals I dot serial.
That's as far as we go.
Okay. It is almost there. In fact, Visual Studio doesn't like this.
Do you need to do the into, join into?
Do we need to do into something like that? It's related to the join. The join is missing something.
So you have to do it where it's on.
Yeah, so we need on, and it has to be on, not where, since we're actually doing a join. T dot ISBN equals I dot ISBN. Okay, good. And you'll notice Visual Studio is even kind of graying this out, these names that I've given it, because that will automatically be the name, since that's the name of the type that was pulled out of the database during scaffolding. Not the name of the type, the name of the field. Okay, and then, instead of returning null, we can return JSON query.toArray.
So can we delete the title equals?
Yep. So we can just select those and just let it use their existing names. Okay, and then when we run an MVC web project, it first of all takes a little longer to compile, unfortunately. Not to compile, it's actually the dynamic startup time. It has to load tons of external libraries. But then it opens a web browser, and let me get a notepad here that has a much bigger font, so we can copy out what we're going to get from the web browser. Okay. So here's what our query returned. So starts with a square bracket, meaning it's an array. Good. We get that book with a serial. We get the Lorax with one serial and another. A couple of Harry Potters, and so on. Good. So yeah, that's what we want. Oops, I don't want to save that. That's what we wanted, and that's what we got. Now we're going to use that as a basis for kind of building up more interesting examples. So let's say instead of kind of repeating the title and pairing the title with every serial number that it has, which is exactly what you would get in a normal SQL query if you wanted that. You would have to just return like every title column and every serial column that matches it. But in C#, you could easily imagine doing this a different way, where you just have a pair of one string paired up with one list. So instead of two titles Harry Potter, I have one title Harry Potter followed by an array of all of its serials. An array or list or something. So we can't really do that in SQL, but we can easily do that in C# and LINQ, and we have to just kind of figure out how to translate that given the LINQ's syntax. So I'll just go back to Visual Studio. And so basically what we want here is we've got this part still correct. We still want to select at least a title out of something. But then the other thing we want to select is something like serials, plural, equals, some kind of array. So array or enumeration or list, we need some kind of multiple item collection. So let's think about that. Instead of joining already, so instead of joining right away, I'm just going to do, well actually, you know what, let me keep this query, comment it out and copy it and then start from there. So this is our starting point, but I'm just going to start with from T in titles. I'm going to hold off on the join for now. Okay, so then we want to do select new title, and then we need an enumeration here, since we want one title to be paired with multiple serials. Well, we know how to get an enumeration using LINQ. Like this whole thing right here, this query, is an enumeration. And turns out you can do nested queries in LINQ just as you can in SQL. They're different, but I can put another nested query in here. So I can just do serials equals from I in database.inventory. Okay, and then I only want the ones that are associated with the title, T. So I'll do where I.ISBN equals T.ISBN.
So don't you need an equals, like EQUAL?
So don't I need the word equals spelled out? No, because this is not a join. This is just a where. So if you're using join on, then you do need the keyword equals. Since this is where, I can just use plain old C# equality operator. And then what we do is we select I.serial. Okay, so what we have is, so I'm just saying for every single title, select the title, and then additionally select something called serials, which is going to be, all of this is going to be an IEnumerable. So I have one title paired with an IEnumerable of serials, and only those serials whose ISBN matches that book. Question? Say that again. Oh, so do I still need this?
Yeah.
No, because the name is already title. So you can see Visual Studio even grayed it out because it's unneeded. I'm not actually changing the name. I do have to specify this here because I want to give this the name serials. If we go to the slide, well, I didn't specify what the name should be, but we should give it some meaningful name. Serials meaning plural. Okay, so that was the old query. Here's the new one. I won't go through all of this. I'll just do enough. So there's the Lorax with one title and multiple serials. So an array inside of this other JSON object. Okay. So if we want nested data, we can just do a nested select. And that's basically what we just wrote in Visual Studio. Okay. Now remember, back when we were talking about scaffolding, we get these automatic links between objects. and it figures these out based on the foreign keys in the table. So if we're looking at inventory and titles, inventory's ISBN is a foreign key pointing to titles ISBN. And because of that, the scaffolding made inside of the class, inside of the titles class, it made a collection of inventory objects. And inside of the inventory class, it made a single title object. Okay, so every title in the titles table can point to potentially multiple objects in the serial, in the inventory table, because I could have multiple copies of that book. But any object in the inventory table can only point to one title because of the direction of the foreign key. So this turns out to be not just a convenience or a shortcut, but very useful when writing link queries. It's not really just to avoid doing a join. It actually makes it so that you can put your, formulate your queries in a much, much cleaner way. So let's kind of look at this. If I were to use that, from T in titles, select new, t.title, comma, t.inventory. So remember, t.inventory is an iCollection. It's all of the inventory entries for that book. So say Harry Potter. If I have 3 copies of Harry Potter with different serial numbers, then the one row out of the title, Harry Potter, will have a collection of all of its inventory entries. So this would return a list of string and then a collection of inventory. But what we want is, and what we just wrote more manually, is we get a string title followed by a collection of serial numbers. So I don't want the entire inventory object which has ISBN and serial number. I just want the serials. So how can we use this navigation and nested selects to do that? So here's basically rewriting that query we just came up with in a much cleaner way. And I'll just do it in code instead of kind of focusing on the slide. So from T in db.titles, select t.title, comma, serials equals from I in t.inventory, select i.serial. So I don't have to do that whole where clause where I'm saying like this serial matches the other serial. That's exactly what this automatically does. This is the navigation link from a title to all of its entries due to that foreign key in the inventory table. Okay, and that gives me basically exactly the same result, but just in a much quicker and cleaner way. Any questions? Yeah.
Would that actually be faster?
Would it be faster in terms of performance? No, it'll actually result in like exactly the same compiled SQL. Yep.
It feels like a circular dependency. Why isn't it?
Feels like a circular dependency?
Just because, titles has inventory and inventory has titles.
So like this right here. It is a circular dependency, but it is handled by kind of making interfaces above where all of these classes need to go. So actually, no, I lied. That's not how it's handled. It's all of these classes are defined in the same DLL. So there's no actual DLL circular dependency. Circular dependency between classes is actually fine as long as those two classes are not in different DLLs that need to be referenced. Okay. So, as was already asked, kind of, is there like a performance difference or any kind of difference between like using a where or a join or something. No. Using this navigation stuff is going to have to result in some kind of SQL join. And the LINQ compiler just automatically figures all of that out, and it is usually smart enough to do it the fastest way. Okay, finally, let's look at what we got out of that query. So those first two look good. Here's one, spinning silver, where it has an empty array of serials, which is correct. My library doesn't have any copies of the book, but it is a book. But if we wanted to change the query, like, I don't care about the books that I don't have any copies of, I just want the books that I have a copy of, then we would basically want to delete this row from the query. So how would we do that kind of in LINQ? Let's just like play around and see if we can like think of how to do that. So you would want to do something like, you know, if t dot inventory is, this is total pseudocode, is empty then and Visual Studio does not love pseudocode. Don't select anything else, select something. And so that's kind of what we want in terms of logic. But when I do select like this, you know, select new something, that is always going to select something. You can't put like a condition inside of here and say either select this or don't select anything at all. You can put a ternary expression in here and say select this or that, but you can't say select this or remove the entire row from the select. It has to select something. You can change what it selects, but you can't remove the option to select something. So let's get rid of this like total pseudocode here. And we'll just put that back to how it was. And using those navigation things that the scaffolding builds in for you is actually a really easy way to do this. So all the way up here, from t_in_db.titles, I can just do where t.inventory, and that's just an IEnumerable, so I can just do .any. Any means, is it empty or not? That's kind of like saying, is size greater than 0? So this will automatically filter out any title, that does not have any associated entries in the inventory, using those foreign key links. Okay? So not really a straightforward translation from this into SQL. You could easily do this in SQL, but it would look very different. So you kind of have to think in a different way when using LINQ, but taking advantage of the fact that you have C# and all of these like collection functions like .any and things like that. Okay. Yeah, question.
Instead of doing t.inventory.any, not that we should, but would it be possible to just compare, where t.inventory.size greater than 0?
Yes. So it wouldn't be size, it would be count, I think. Yeah.
Okay.
Okay. So phase 3 is coming up, and basically you're going to be implementing controllers in these 4 files. These are the main controller files, and within them are individual little functions. So things for creating a new account, and then, so that's kind of not specific to any type of user. It's not specific to students or professors. Anyone can create an account. And then controllers specific to students, so like submit an assignment. And then specific to professors, grade an assignment, or things like that. And in there, let me kind of recap again a little more. You're going to be doing a lot of like inserts, deletes, selects, things like that. So remember, inserting in LINQ is super clean and easy. You just make an object of the type that was scaffolded out of the database, and then just say database.add, and then database.savechanges. And then that turns into an SQL insert. Deleting, almost identical, except you remove instead of add. And you're just removing from a collection, a C# collection. Okay, but what about update, just changing an existing row? So you might want to do this if the student submits these to the same assignment again. So like they can submit once. If they make another submission, it doesn't create a new row. It replaces the existing row with different submission contents. And it's basically, find the object, the existing object by doing a select, and then change it in some way, and then just db.savechanges. So you're not doing an add or a delete. You just like get the object into C# and then save changes after modifying it. So this is pseudocode, but what this would look like in real code, say I'm changing the name of the person with card num 1, I'm changing their name. So first I find the person with card num 1 by doing a standard select. And then, so this looks a little weird, query.toArray0.name equals Joe. And I have to do that because any LINQ query is going to return an enumerable. So it's not just going to return one object, even though I know there's only one person with that card num, it's still going to be an enumerable. So there are lots of ways you could do this. You could do like query.first, query.get0, query.toArray0, and then I've changed the object, and then I just do save changes. It'll automatically go and update that row. So this part of it, though, this like .toArray0, this is messy. It works, but it's messy, and there are just better ways to do this. So enumerable has a thing called single or default, which means you're kind of expecting there to be either 1 or 0 things in the enumerable. So if there are 0, it'll result in default, which in LINQ terms means null. Otherwise, it'll just give you the object. So do that, put in a check if x is not equal to null. And let me back up a little bit. This is also missing a safety check. This is assuming that the query has at least one object in it. This would just crash if it didn't. So, kind of rewriting it this way, use single or default, that's kind of forcing you to think, okay, well, it might actually be null, so check for null. If it's not, update it, and then save changes. Okay, so lots of little just convenience functions. And this is not specific to database. This is just specific to C# enumerable interface. But a lot of the controllers you'll be writing for your LMS, you'll expect them to only return one thing. So functions like single or default or .any, things like that will be very useful. Okay. So the only major component missing now from phase 3 is how are you going to handle user accounts? So remember the LMS diagram just like completely left out passwords intentionally because there's a little more to it than just saving a password in a database. So anything with user accounts, such as a web server, you have to have some way of verifying that they have typed in a username that matches whatever their password is before letting them access their account. So conceptually, it's really easy. In theory, it kind of just looks like this. You have some kind of users table or users collection. So first you just check like whatever username they typed, is that in there? If not, return an error. If it is, then go one step further and use that username as a key to look up into some passwords dictionary and make sure the password they typed matches the password that you have saved when they created the account. If not, invalid password. So in theory, very simple. In reality, this is not quite safe enough. This is very vulnerable to attacks. So that will be the final kind of missing piece before you can start working on phase 3 that we'll talk about today. But let's take our short break first before switching gears. Is the username in that column? Does the password they typed match the one on that row? So you could do something like, here would be like the SQL query. So select username and password from this table where username equals what they typed and password equals what they typed. And then if that query returns exactly one row, well, it could return more if 2 people have the same. No, you would say a username is unique, so this should return exactly 1 row. If not, they've typed something wrong. So remember, a database for a web server, you have your password to the web server, like you have your Canvas password. You do not have a password for Canvas's database. So you cannot go and just start selecting rows out of their users table. So that's good. You can't go and look up these passwords. Good. So it seems like this is fine as long as the web server is the only thing that has access to this table. Then all is well. In a perfect world, this seems okay. However, we've seen ways to kind of steal information out of a database. Injection attacks being one. This thing called social engineering, which we'll talk about a bit, or even just imagine a physical breach. Somebody is getting a tour of Canvas's instructor facilities, and they notice that somebody left their workstation unlocked with the MySQL terminal open, or something like that. So you walk in and you start stealing passwords. Turns out these bottom 2 are actually more common attack vectors than injection attacks. So hacking is not actually like they make it out to be in Hollywood, where you're typing code live, while someone else is typing code live and trying to block you or something. It's mostly this thing called social engineering, which is not as fun as you think. So the attacker just calls up some database administrator and says, "Hey, I'm from IT and we're working on an important problem and I need your database password." And they are wisely reluctant to give out their password. And then the attacker kind of starts threatening, knowing some kind of personal information, "Oh, I know who your manager is. I'll just call up, I'll call up Sally and tell her you're not cooperating." And they're like, "Whoa, they know who my manager is. They must be legit." And so they start panicking, and they're like, "Okay, don't get me fired. I'll give you my password." This is actually the greatest threat to security is attacks like this. Not even anything technical to it. Anyone seen the show Mr. Robot? So, great thing about that show is they actually talk about this as being one of they're like, well, we need to do the social engineering part first. You can't just go and steal any information you want magically. Okay, so the unfortunate reality is that tables can get stolen out of a database. So if you have a table that contains usernames and passwords, you have to assume that it could be stolen. That's fine for most tables. Say they steal the checked out table, they know who has what books checked out. Maybe kind of bad, but not really a disaster if that table gets stolen. If the password table gets stolen, maybe not even that. You might be thinking maybe not even that bad. Big deal. They can log into my library account. But passwords, the way that people use passwords is your library password is probably also your Gmail password and your bank password. So if they steal your library password, they now have your password to probably a lot of other things. If they get your Gmail password, they can now do a password reset on all of your other accounts, which probably goes through Gmail. And so they can reset all of your other passwords and steal all of your accounts. So passwords are very dangerous. You do not want them stolen. So what we do is we don't store username and password. In fact, we don't store the password anywhere, not even on the server. Question?
Why can't you store the username?
You can't. You do have to store the username. Was that the question?
Yeah, you said you don't store the username or password.
I misspoke. If I said they don't store the username or password, they do store the username, definitely. They do not store the password. Like not even the web server knows your password. How then does it verify that you have typed in your password correctly when you're trying to log in? It can do this verification, so how is that possible if it doesn't even know your password? It's not just that the server doesn't know your password. It does not exist anywhere except for in your head. Like Mark Zuckerberg could not tell you your Facebook password if he wanted to. So obviously it has to save something that can tell you whether you have typed in your password correctly. It saves some other form of it. So here's kind of how it works. When you're creating an account, you take the plain text password and you run it through some scrambler. And so that's going to produce like some random looking hex string. Not random, but just looks like garbage to any person. And then you save that in the database, not the plain text password. Okay? And then when you're logging in, you take the plain text password that they typed, run it through the scrambler, compare that to the scrambled password that's saved in the database. So if the scrambled versions match, then you say that was a successful login. So there's some issues here. Like, how does this scrambler work? What are the rules it has to follow in order to make this work? First of all, it has to be consistent. If I created my account like a month ago and then I try to log in now, this scrambler cannot be based on like a random number. It has to produce exactly the same scrambled key that it always will produce given the same input. Okay, and then, so let's say the database gets stolen. So I am saving this in the database, and tables can get stolen. So let's say it does get stolen. Now all they have is some garbage. They have some scrambled string. What can they do with that? Let's say, well, maybe they can like run it backwards through the scrambler or something to get your password back out. Because what they need is the password. This scrambled key does not help them. You cannot use that to log in. No, you cannot do that because this scrambler function, whatever it is one way. If I take that scrambled version and I put it back through the scrambler, it's just going to scramble it even more. So has to be consistent, cannot be reversible. If I take a scrambled password, I cannot possibly reverse engineer that into what the original password was. So in other words, it's a hash function. So it has to produce the same result given the same input, just like a hash function. Has to be unreversible, and has to be very unlikely to produce collisions. So whatever this function, this scrambler is, it has to follow these three rules. Basically, from now on, we'll call it a hasher. Okay, so not just following the rules of a hash function, but also for security reasons, it has kind of extra strict rules. And that makes it, we call that a cryptographic hash function. This being unreversible part in particular is very important. Well, both of these, 2 and 3, are very important here. We cannot, if I steal a scrambled password, a password hash, It has to be very hard for me to figure out some string that produces that hash when passing it through the hash function. Okay, so let's look at an example. Let's say my hash function is, just take the binary of whatever their password is and set every other bit to 0. Okay, so that will change, whatever they type, that will change it into something else. And I'm gonna work with just little numbers here. So the small integer 158. You could do this on strings too. Strings are just bits. So ignore the fact that we're dealing with just a small 3-digit number. So say my password is 158. If I write that out in binary, it's that. My hash function turns every other bit into 0. So my hashed password is 136. So if somebody steals the table, they get 136. They don't get my actual password. Okay, is it consistent? If I pass in 158 into that again, will I get the same hash back out? Yes, it's not based on time or randomness or anything. It'll always produce the same result. Okay, is it reversible? If I have a hash 136, can you tell me what the original password was? No, like you can tell me what part of it is. You can tell me that it had a 1, a 0, a 1, and a 0, those black digits, black bits. But you cannot tell me what the original ones were, every other one in between. So I can get those ones back. The rest of them are question marks. So I could easily, though, start filling things in here. I could say, well, just fill in a bunch of 1s there. And that would give you one possibility for what the password was. So maybe I fill in a bunch of 1s, I get 221. Maybe I fill in maybe I fill in 0111, and I get the actual password back. Okay, does that really matter though? Like, there's still a lot of possibilities here that they would have to try before figuring out my actual password. But let's look at this. So let's say my actual password is 158. So the stored hash is 136. If they type in 221 as my password when trying to log in, will it let them in? Yeah. The hash function doesn't know that that was not the right password because it is the right hash. So problem in multiple regards here. First of all, they could log in. There are a lot of passwords that will let them log in to my account. They still may not know my password, but they could log in. The other problem is if they really need to know, if they don't care about logging into this account, but if they want to know my password to try to use it somewhere else, there are not that many things they would have to guess in order to figure out the actual password. So this, just set every other bit to 0 is a very bad hash function in terms of cryptography. It would work, but it would be very insecure. So although I can't tell you what the password was, I can easily find a colliding password that will let me in. Okay. So it has to follow additional rules. It has to be extremely difficult to find a string that produces a known hash. If I steal a hash, it has to be basically impossible to figure out what the original password is that produced that hash. So it has to be truly one way. And collisions, this is kind of the same idea, but collisions have to be very unlikely, even for similar passwords. So even if one character is off, it has to produce a wildly different hash. Okay, so even with a good cryptographic hash function, it is impossible to completely get rid of collisions. Right? There are an infinite number of passwords, and there are a finite number of hashes. If your hash, say, is 64 hex digits or something, there are only a certain number of possibilities. There has to be collisions. There has to be another password that will actually result in your same hash. So you could actually potentially log into Facebook by typing some complete gibberish if it happens to hash to the same secret hash that your real password does. But in reality, that's an impractical attack, because it would take so long to find a collision that it wouldn't even happen in your lifetime. So, okay, what is this cryptographic hash function? Obviously, we don't use set every other bit to 0. We won't really go into the details of how to make a good cryptographic hash function, but there are a lot of them that smart people have figured out. This MD5 one was popular for a long time, and then turned out they discovered lots of flaws with it. So it's hopefully not used anymore. These other ones are. Some of them are considered better than others, but they're all still kind of in the running. So how can we do this as designers of our own LMS? So you want to take in some password that somebody typed and save not an encrypted, a hashed version of it. So in C# you can just do, using this built-in library, SHA-1.compute-hash password. That'll return a new string that is the hashed version. Or in SQL, actually even directly supports this. There's a function, SHA-1, in SQL, so I can do insert into some table, SHA-1 on their password. And what it returns is just plain text. So you're not saving like raw binary or anything, you just save like the plain text hash of the password. Yep.
When is the SHA-1 called in the SQL version? When is it
called in the SQL version? At some point when the engine translates your query into actual procedures, it'll just do it before actually inserting it into the column. So this is account creation time, because you're doing an insert. If you were doing a lookup, you would do something like select where SHA-1 equals, pull the column out of the table. Okay, so there are still vulnerabilities. Passwords get stolen. Like you hear about this every once in a while. Credit card numbers get stolen. Passwords get stolen from various big companies. So what is it? Are they just not doing this? No, they are definitely doing this. So how are passwords still getting stolen? And we're kind of at the point where we are now, where we're saving a hashed password. This is like the beginning of the arms race, the hackers versus the security devs. So let's say this table does get stolen. So they have plain text usernames and they have hashed passwords. Can they do anything with that? So here's one thing to try. Assume that noob users will use some common password, and they know what the common passwords are. This is actually 1, 2, 3, 4, 5, 6. I pulled this off of a real list of common passwords. The string password is a very common password. So what you do is you take the top 100 most common used passwords and just pre-compute their hash. So, and you just make a table. So this pre-computed common passwords plus their hashes is called a rainbow table. All you have to know in order to make this table is what hash function is the web server using. And it's a safe bet that they're using one of these or something like that. Okay, so they make a rainbow table. Question first?
Do hash functions not have a seed you could pass in?
Do hash functions not have a seed you can pass in? So yes, but then all the attacker has to do is also steal the seed. So it's that does add one kind of extra barrier, but these extra barriers that don't actually, that are not hard barriers, impassable barriers, is basically nothing. If they gain access to your database, they can get all of it, including the seed. So what they do is they take their rainbow table and just compare it to the stolen hashes, and once they find a match, they know your password. Okay? So that's attackers +1 in the arms race. So how do we fight back? We use, so question first.
How do they know the hash function?
How do they know the hash function? Right. So they can just guess is one way. Another way is maybe they have a friend who works for. Maybe they did some social engineering. They have a friend who works for the company, and the friend didn't mean any harm by it, but happened to mention, oh, we use SHA-5 or or SHA-256 or whatever. So the next step in combating this rainbow table attack, is we add something called salt to the password. So it's like a breakfast themed security. You've got the hash, you salt it a little bit. So what this is, you take the password that they typed when at account creation time. You take their password and you just add some random stuff to it. So salt equals random string. Prepend that to their actual password. So if their password is bad password, the thing that you're going to pass into the hash function is now A748CF7A3 bad password. So you pass that whole thing into the hash function, and now you get a new hash. So this hash now, even if they tried a common password, like bad password, they would not get the same hash out because this one has been randomly salted. So the standard rainbow table is useless. Let me go back. This rainbow table that they pre-computed giving certain passwords and their hashes is useless because the actual passwords have a bunch of random stuff on them. So I'll get to you in a second. So let's kind of just look at how does this work now, and how do we log in? So this is the creating an account part. We start with a function that now does the hashing and salting, so it has two inputs, your password and a random string. Produces a hash, and you save that in the table. Okay. Now how do we log in? So if the hash that we produced at creation time had some random component to it, then when they're logging in, how do we reproduce that random component? You might think, well, just reset the seed, use the same seed or whatever, but if they steal the seed, then the salt is useless. So instead of using a random string at login time, what we actually do is save the unhashed salt alongside the full hashed password. So this salt now, that it looks like a hash, it's not. It's just a random string in plain text. And the hash is the salt plus password run through the cryptographic hash function. So how is this any better? If I'm just saving the salt in plain text right alongside in the very same table, if an attacker steals it, they get the salt. So here's basically what they do, is they make a much, much bigger rainbow table. For every stolen salt that they got out of your table, they pair that up with every common password and produce a hash. Okay, so look at this column on the left here. Every third one is filled in because it's basically all stolen salts multiplied by all common passwords. So their rainbow table just got much, much larger, squared larger. But still, in theory, you could do it. And then they just take all of those possible hashes, compare them to the stolen hashes, and once they find the one that matches, you can basically throw away the salt, but now you know their password. Was there a question back there?
I was just wanting to ask about the user about the address.
Okay. So let me kind of back up a bit. I kind of skipped over this. So when we're logging in, we have to have the salt saved in addition to the hash in order to combine it with the password they typed at login time in order to reproduce the correct hash to know if to know if we can let them in. Was that a question? No.
Yeah, it's like we have to store the salt, right?
Yes. So we have to store the salt, meaning the attacker can steal the salt. All we've really accomplished is made their job harder. They have to make a much bigger rainbow table. It'll take longer to compare that to all the stolen hashes.
Could you just update the salt every time they log in?
So could you update the salt every time they log in? That would be, yeah, so that would be one possibility, and then they would have to steal the table again. Like if they fixed the breach and they have an old table, yeah, that would be one possibility. But, so here's kind of so let's see, we went attacker +1, defender +1. Attacker can still do a rainbow table since computers are fast. So how can we improve security on the defender's side? Well, a rainbow attack is basically a brute force attack. So how do we hurt a brute force algorithm? Just slow it down. So the algorithm I'm talking about is, well, the algorithm is for a ton of combinations of hashes and of salts and passwords produce a hash. So that part, the produce a hash part, is the only part we have control over, and that's the part we need to slow down. So basically we intentionally slow down the hash function, not by putting in like a sleep or something like that, because that would not actually do it. They could write their own version of the hash function and just don't sleep. You have to make it like inherently computationally intensive in order to slow it down. So like a good cryptographic hash function should take about 1 second to run. So, you know, when you log in, it slows your login down by like 1 second, which is not a big deal. But it prevents, say your hash function originally was like 1 microsecond. If you slow it down to 1 second, you've now made the brute force attack 1,000,000 times slower and impractical. So it now will take like months or years instead of just like hours. So this is what .NET actually does. You can call SHA-1 directly, but if you actually make a .NET Web Server project and say, give me the capability to create passwords, it actually does this. So it salts your password, runs SHA-1 on it once, and then just runs SHA-1 1,000 more times, using the output from the previous iteration as the input. So the point of this is not to make it like more hashed or more scrambled. It's just to slow it down. You're doing 1,000 times as much work. And there's no way to skip this. You can't just say, all right, I know we're going to run the hash function 1,000 times, so create a version of the hash function that just does that all at once. You can't. You don't really know what the output of a hash function is going to be until you run it. So you have to run it 1,000 times.
So why isn't the salt just considered like part of the hash algorithm?
Well, so the hash algorithm itself is just the scrambling part. But the salting is part of what's called a key derivation function. So a KDF is do all this stuff like salting and running the hash 1,000 times. That's all part of something called a key derivation function. The hash itself is not necessarily even for passwords. It's just like take in some input, produce some scrambled output. So we just kind of classify them separately.
And then also, how does I guess I'm kind of confused about how salting actually makes a hacker's life more difficult, right? Because it's like if they have the list of common passwords and they also have the list of all the salts for each entry.
Yep.
Or have it, I don't know.
So you have a common password. You have the salt. So you have user X. This is their salt. This is the hash of their salt plus password. Okay. So given that hash, you do not know what the input to that was. You cannot reverse a hash. So you have to somehow figure out what is the salt plus their password. if you've stolen the table, you only have the salt, which means you're still missing the password part. So what you have to do is make this table where you say, given the known salt, and I don't know the password, combine that salt with all of the common passwords. That makes up all of the possibilities that I have to compare to the stolen hash. So basically all it's doing is increasing the number of things they have to try before they can actually figure out the password. Instead of trying it against all of the known passwords, they have to try it against all of the known passwords times all of the hashes.
So the longer the password, the harder it is to crack down. That's the lesson.
The longer the password is, it's not really the length, it's a little more like the commonality of the password. You could have a really long password, but if it's common, it's still a bad password. The length of the password doesn't actually really affect the quality of the hash that you get out.
So the salt is something that's not common, and when you attach it to a common password, that makes it uncommon.
Yeah.
Okay.
Well, it makes it, it multiplies the amount of work that an attacker has to do in order to figure out all of the passwords that they stole. Okay. So we were at the point of slowing down the brute force attack. Slowing it down is also is good, but you can also just use an algorithm that necessarily requires tons of memory. So, like GPUs are really good at computing hashes, and they have vast computational power. So even with like a slowed down brute force attack, throw a bunch of GPUs at it and you can still do something with it. If you make the algorithm so that it just requires tons of memory, that really hurts GPUs because their parallelism requires every thread to be fairly small in state. Okay, so even still, arms race continues. If you throw a lot of computation at it, you can still do a giant rainbow table. So we add pepper to the breakfast security. This orange box here is now the function whose job it is to produce a key. So it inputs the plain password, it inputs a random salt, and it inputs pepper. The idea is it's similar. It's a string that you prepend to the password before hashing in order to just kind of change it even more. But what we do, so we could do that a bunch and just keep going with that. But the idea behind pepper is that it's stored somewhere else. So you don't store it in the users table. You store it like in a completely different database, or even just in like a config file on the server or something. So if they happen to steal the database but can't get access to the pepper, then there's still nothing they can do. So we take all of those things combined, hash it to produce the key. So basically the idea here is salt is randomly created at user account time, and it has to be unique per user. Then the pepper part is basically you just need one string for the whole system. So you have one like fairly short string just saved in some file somewhere that the server has access to. And the reason this adds security is it's just two places that have to be attacked now instead of one.
So, like in the case of a security breach, if someone did get pepper, is there any like reasonable way to change it for everyone, or would you basically change the pepper and then rehash everything?
Right. So if they did steal the pepper, you would have to go and change it and then rehash everyone's passwords. And one easy way for pepper to not work is to use the same one on like all of your systems. So like if there was just if Facebook used the same pepper for Instagram and for Facebook, then that would kind of kind of defeat the purpose. If they stole one, then they get it for the other. So all of this stuff goes into the what's called a key derivation function. Salting, peppering, hashing, doing it very slowly. There are lots of ways to make a key derivation function. Question?
Suppose the pepper is physically written on a sheet of paper that is placed under a computer scanner that physically scans the paper every time it needs to use the pepper.
So if you write the pepper on a piece of paper inside of a scanner, that's one good way of removing it from the internet. But it's still vulnerable to like physical breaches. If the scanner is in any way vulnerable, then lots of interesting things to think about when it comes to security. Okay, so this orange box here is basically the KDF. So, in summary, the biggest vulnerability is bad passwords. Like the only reason any of these attacks exist, at least the ones we've talked about, rainbow tables, is because people use common passwords. So don't use a common password first of all, and then you're pretty safe. But that's good enough for you as a user. That's not good enough for us as developers. We can't force all of our users to be good users. So use a good password, but we as developers have to assume people will not use good passwords, so we have to do all this stuff, salting and peppering and hashing. And then if your password does get stolen, even if it's not that common, if it's kind of fairly common maybe, you're safe for a while, because these brute force attacks, these rainbow attacks, take a long time. Which means if you hear that some big company says we had a big breach, you should go change your password, even if it was like a week ago or something. Because by the time they get through their whole rainbow table, if you've changed your password, then it does them no good. Okay, so for us, for the LMS, we're going to want to do all of this, but Visual Studio and .NET MVC projects have this all built in. So you configure your project with identities, which is like user accounts, and where we store all of this stuff, like the salt, the user, the hash, it has to go in a table somewhere. And to keep it separate, we actually just make a whole different database. So you'll have your LMS database, which has like classes, assignments, everything like that. And then you'll have your LMS users database. So not just different tables, actually different database. And we don't have to worry about what kind of tables and columns do I need? What are the types of the columns and the sizes? .NET has a tool that will automatically set it all up for you. So here's Visual Studio. And remember this shell. So Visual Studio has like its own built-in console that we were using to run the scaffolding tool. So I can type in commands in here that do things. There is a tool that will automatically, you point it at a database, and it will automatically go and create tables in that database that Visual Studio needs for its user accounts solution. So I won't actually run it. I'll just give you the command you need to run. It's kind of like the reverse of scaffolding. It's go and create some tables instead of read the tables and create classes. So here I am in MySQL. I'm going to do use LMS users 2. This is just my kind of temporary one because I don't want to mess with the real one. But notice it's not LMS, it's LMS users. So after running that command from Visual Studio that would create those tables, we get a whole bunch of ASP.NET tables. So role claims, roles, users. So I'll do like describe ASP.NET users. And we get a bunch of columns in here. An ID, that's kind of just like a primary key. It actually just stores your username, email and stuff like that. We won't use most of this, but there it is, a column which just stores your plain old password hash. It even tells you what the column is called. Like, it's not even trying to be obscure at all, because the security comes from something else. So back to, so here's another one, ASP.NET roles. Well, the formatting's a little bad here, but here's a role student, here's a role professor, and here's a role admin. I had to configure it, when I created these tables, I had to configure it in a way that it knows what the roles are in my system. So, and then in the web server, I can just tag a function. I can just say, you have to have this role in order to access this controller. And when you log in, this system automatically knows if you have access to that role. So let's look at, let me go back to users. Let me select star from password hash. Oh, from, that's not right. I want to select password hash from ASP.NET users. And so there it is. If I was an attacker and I stole this, this is what I would get. The salt is in here somewhere. The pepper is in here somewhere. But we can't really do much with it. Well, we can't. We could make a rainbow table. If somebody had a bad password, then it's still vulnerable. Okay. So that's kind of the final missing piece before phase 3. You're going to make a totally separate database that will handle users in terms of being able to log in. The only thing between those two databases will be a UID. So you will have your own UID in your LMS tables, and the user name, I guess that's one more thing I should show you. Select user from ASP.NET users. What's it actually called? Username. So these are the 3 users I've created so far. Exactly a UID in the same format that your web server needs. So you can basically use that as a key or a pointer to your users tables, where you actually have a professor table that says the professor works in this department or whatever. That is not included in the roles and passwords tables. This is the only link between the two. Okay, that's it for today.